till last lecture we have learned ellipse, we have completed all concepts and we closed it. Now the omen is on to you to prepare and practice as many questions as possible to develop problem solving skills. Now in today's lecture we will start with hyperbola. So as it is first lecture, we have to learn lot of fundamentals, and as I keep saying, it is essential that you learn all fundamentals with the right mindset and with right approach. So if your basic concepts and fundamentals are clear, then you can proceed with the next advanced concepts, and while you solve problems and while you learn advanced concepts, your conceptual clarity will be high if your fundamentals are good. Okay. So let us learn some fundamentals today. Okay. So first, what is hyperbola? So just like the way we have defined parabola and ellipse, we can also define hyperbola in similar manner. So basically here we have a fixed point which is called as the focus. Fixed point S is the focus, and we have fixed line L as the directrix. Now the point P is a variable point which is moving, so that PS and PM, that means distance from fixed point and distance from fixed line, are always at a constant ratio which is named as E, which is the eccentricity. Now for hyperbola, E must be greater than 1, for ellipse E less than 1, for parabola E equal to 1. Now we know already this idea, and that is how we define. Now the point which is closest to the directrix is the vertex. How do we define vertex? Vertex is the point which is closest to the directrix. So here this is the point which is closest to directrix. We can name it as A, which is the vertex, and passing through vertex and focus, the line that is perpendicular to directrix is always called as the axis of the conic. Now here in hyperbola, this axis is called as the transverse axis, okay, and in ellipse it is called as the major axis, in parabola it is called as the axis of the parabola. So these are the fundamentals. Now we need to understand the shape of the hyperbola before we even derive a standard form for hyperbola. So let us understand the shape of the hyperbola. So before we understand the shape, so let us also first understand this general equation. So this general equation of second degree represent hyperbola if delta is not equal to 0 and h square is greater than AB. Now delta means you already know, it is the all hot girls having boyfriends go for cinema. If this delta is 0, then the general equation represents POSL, pair of straight lines. Otherwise, this may represent a conic. So delta must be not equal to 0 for this to be a hyperbola, and then we will check h square is greater than AB or less than AB. Okay, so this is the procedure. So this is very simple idea. Now when it comes to the standard form, before we go for the standard form, it is better that we understand the shape of the hyperbola. So in hyperbola there are always two branches. This is one branch, and there is also another branch like this. Okay. So there are two branches of hyperbola, and these two branches will never meet. They will never meet. Okay. And this S is one focus, S dash is other focus. There will also be another directrix here. There is one directrix here, there is another directrix here. There are two directrices, there are two foci, there are two vertices. Now the chord which is perpendicular to the transverse axis and passing through focus is called as the latus rectum. So there are two latus rectums in this also. So, when there is plural, we call them as latera recta. Okay. And the reason why we call this AA dash as transverse axis, this is called as the transverse axis. The reason is this. So, suppose let us say we have two branches like this. If we have two branches and the line which is joining the shortest distance, these are the closest points. This is acting like a transversal. If you remember the straight lines, if there are let us say two straight lines, the line which is intersecting both of them like this is called as the transversal. So, the line which connects both the branches which are completely opposite is called as the transversal. So, that is why we call this axis as transverse axis. Okay. So, there is a reason why we call it as transverse axis. So, here is the reason. Okay. So, this AA dash is called as the transverse axis because it is connecting both the branches. Okay. Now, there is also another axis which is called as the conjugate axis. Okay. So, conjugate axis, we will understand this little later, but let us first learn the terminology. So, conjugate axis is generally defined as BB dash. Okay. So, we will note these points little later. AA dash is transverse axis, BB dash is conjugate axis. Now, we know that it has two branches and there are two vertices, two foci, two directrices. Now, whatever is the point of symmetry, that point is called as the center of the hyperbola. So, this C is the center. Now, here we have understood basic idea. Now, all chords that pass through focus are called as focal chords. From center if they pass, central chords. So, from center if we join any point, radius vector. So, all the ideas are same. So, whatever we have learned in ellipse can be applied in hyperbola, especially when it comes to the setup. Now, you will also see that algebra is also very much similar, just like an ellipse. We can say that ellipse and hyperbola are basically cousins. So, whatever are the ideas that you apply, similar ideas can be applied in hyperbola also. Okay. So, now to derive a standard form, basically till now we have understood the simple idea of what is there in the hyperbola, that we have understood till now. Now, to derive a standard form, we need to take this entire setup and place it at the origin. Why do we prefer that? Because we want the standard form in a simplest form. So, to gain a simplest equation, we place the entire setup at the origin. So, basically we take the center of the hyperbola as the origin. So, this I will explain in the next page. So, we have another branch here, we have one branch here. Okay. Now, this is S dash, this is S. There will be one more directrix here and this is the center. So, we place the center at the origin and we take the transverse axis as the x axis. Okay. And we take the conjugate axis which is supposed to be passing through the center and perpendicular to the transverse axis. This is the conjugate axis. We take this as y axis, x axis here and y axis here. Okay. Now, we will start defining the points. So, where do we start? If you remember the ellipse, we assume some points. So, which points do we take? We take A and A dash as a comma 0 and minus a comma 0. This is what we are defining them as. So, A can be written as a comma 0, A dash can be written as minus a comma 0. We fix A and A dash. Okay. And then we set up S and S dash. How do we set up? We already know that E is greater than 1. So, out of these two, AE and E, which is bigger? AE is bigger than A because E is already greater than 1. And here if you notice, from the origin if you move in this direction, A comes before S. So, S must be in the closed region of the curvature. If curvature is bending like this, then the focus must be within that curvature. So, because here the curvature is towards this direction, so focus must be here. If the curvature is like this, focus must be here. Okay. So, focus is coming after the vertex. So, we define AE as the focus. So, that means here S can be taken as AE comma 0 and S dash can be taken as minus AE comma 0. So, if you remember, we are setting up origin, we are setting up the center, we are fixing A and A dash, we are designing S and S dash. Okay. Okay, next, because A is a point vertex is on the hyperbola, it must satisfy the definition of the hyperbola. What is the definition? Distance of A from S, distance of A from the directrix, these two must be in the ratio E, which will give me the point on the directrix, which is also called as the foot on the directrix, as A by E comma 0. This we have explained in ellipse also. So, we can take this equation as x equal to E by E, A by E. Similarly, the other directrix will become x equal to minus A by E. So, now two directrices I have defined. Okay. So, more or less we have defined whatever is required to derive the standard form. Now, let us attack the standard form. So, if there is any variable point P here, which is let us say x comma y, it must satisfy the definition which says this distance and this distance are always at a ratio E. So, what do we get here? Root of x minus AE whole square plus y minus 0 whole square divided by mod of x minus A by E must be equal to E. So, this is the definition. Now, if we simplify this, we will get equation of the hyperbola. But if you recall ellipse, isn't it the same equation that we have written in ellipse also? Of course, it is the same. So, equation that we will get will also be same. Let us observe that also. So, here if I square it up and simplify, so these are the terms I am going to get. Okay, so this is my LHS and RHS will become E square into x square minus 2AXE plus A square. So, 2AXE will get cancelled and I take all constant to the other side and variable to the other side. So, what do we get? X square into 1 minus E square plus y square is equal to A square into 1 minus E square. Now, if I divide with A square into 1 minus E square, what do I get? X square by A square plus y square by A square into 1 minus E square equal to 1. See, if you notice, we have got the same equation, but the only difference is E is now greater than 1. Because E is greater than 1, E square minus 1 is positive and 1 minus E square is negative. So, because this value is coming out to be negative, so we will not take this as B square. In ellipse, we take this entire term as B square, but in hyperbola, we take this entire term as minus B square, just to counter the minus sign. So, that means the standard equation will look like this: x square by A square minus y square by B square equal to 1. This becomes our standard equation. So, that means what is B square here? B square is B square is basically equal to A square into E square minus 1. Okay. So, in ellipse it was A square into 1 minus E square. So, now what we will do is we can also derive a formula for E. I will just write it here. So, E equal to, it becomes root of 1 plus B square by A square. So, in ellipse it was minus sign, but in hyperbola it is plus sign. So, we can understand here also that the difference between ellipse and hyperbola is only one term, which is in place of b square we are writing minus b square. Okay. So, this is the overall setup and standard form. If you also want to make a note, you can definitely take a note here. Okay. So, next, so now that we have got the equation, we can find the other points that are required. Okay. For example, let us say you are interested in the points where the curve cuts y axis. So, that means you have to put x equal to 0. So, if you put x equal to 0, you will get y square equal to minus b square, that does not have any solutions. So, curve does not cut y axis. Now, let us say you are interested in finding the ends of the lattice rectum. So, what do we do? In place of x, we will put AE, because here okay. So, let me just explain it here. So, here let us say I want to find these two ends. Now, we know that this focus is AE comma 0. So, these 2 points also will have x coordinate as AE only. So, in that equation, in place of x, I will just put AE and I will solve for y. So, what do I get now? A square will anyways get cancelled. So, I will get y square by b square equal to e square minus 1, but e square minus 1 can be written as b square by a square. So, which further will give us two values of y, which are plus minus b square by a. So, that means this point is AE comma b square by a and this point is AE comma minus b square by a. Now, if you recall, in ellipse also coordinates were same, and what is the length of lattice rectum here? Length of lattice rectum is 2b square by a. So, that is also same. So, setup is almost same. Okay. Now, what is this b? What is the significance of this b? That we will try to understand. So, suppose let us say through C, if I draw a line which is perpendicular to the transverse axis, which has two ends, one end as 0 comma b, other end as 0 comma minus b. Now, what are these points and what is this BB dash representing? This BB dash is called as conjugate axis. Why is it called as conjugate axis? That we will see little later. But what is the significance of this conjugate axis with respect to the hyperbola? B and B dash are not definitely the points at which curve intersects y axis. Of course, curve does not intersect y axis. So, B and B dash are not on the curve, but they will, this BB dash, this length, this will definitely tell you the orientation of hyperbola, whether hyperbola is wide or whether it is compressed, whether it is stretched hyperbola or whether it is compressed hyperbola, that is given by the length of BB dash. If BB dash is very high, then hyperbola is very much wide. If BB dash is small, then hyperbola is very much compressed. For example, we can also take cases like this. We can also get hyperbolas like this. Okay, we can also get hyperbolas like this. So, here if you take the conjugate axis, it will be very small conjugate axis. But if we take very high conjugate axis, let us say I have taken very high conjugate axis, then the hyperbola will be very much wide hyperbola like this. Okay. So, basically this conjugate axis BB dash here and this conjugate axis BB dash here is basically telling you about the shape of the hyperbola, whether it is stretched one or whether it is compressed one. Okay. Now, how is it talking about the shape, that we will see little later. Okay. So, now here we have understood what is the setup, what is the standard form, how to derive it, and also we have observed that in ellipse and hyperbola there are lot of similarities. Okay. Now, next. So, in this standard form of hyperbola, x square by a square minus y square by b square, if you just quickly revise all of them. So, what are all happening here? This is one directrix, this is other directrix, this is our conjugate axis, A dash is our transverse axis, S and S dash are our foci, O is our center because we have fixed it at the origin, and we have, because this we have taken as x axis and because this we have taken as y axis. Now, we also have other special chords which are double ordinates and double abscissa. Okay. So, what are the double ordinates here? So, all these lines which are chords and which are perpendicular to the transverse axis are called as the double ordinates, and all the chords which are parallel to the transverse axis or perpendicular to y axis are called as the double abscissa. So, there is double abscissa, there is double ordinate, and rest all are same. Okay. So, we have latus rectum. Even if this is, let us say, a rotated hyperbola, all other points like foci, center, vertices, ends of latus rectum, all these are valid, but there double abscissa, double ordinates do not exist. Okay. Okay. So, we have understood the basic setup. Now, let us look at all the coordinates in a formulated manner. So, these are the characteristics. So, what are they? Center, we have fixed the center, this is part of the setup, and vertices we have fixed, foci we have designed, and equations of directrices we have derived, focus we have designed, and directrix we have derived. Transverse axis is 2a, which is the distance between A and A dash. Length of conjugate axis is 2b, and also we have learned the importance of the length of conjugate axis. If it is high, hyperbola is very much stretched. If it is low, hyperbola is compressed. Next, relation between A and B, of course, with help of eccentricity we can connect them, and this is the formula for eccentricity. Next, length of latus rectum is 2b square by A. We have understood this. Next, ends of latera recta, we have understood the ends of latera recta, we have also derived two ends. So, other two ends also can be derived in similar manner. Next, focal distance, just like ellipse, here also you have one formula for focal distance. Now, in ellipse, if you remember, the difference here is this minus sign. Earlier, if S dash P was Ex1 plus A, this was different, it was A minus Ex1, but here it is Ex1 minus A, that minus sign difference is there. Now, rest all are same. And there is this important property which is the 11th property. Suppose let us say if I have taken a point here P, so from S the distance which is SP, and from S dash the distance which is S dash P. So, difference of these two is always equal to 2a, which is the length of transverse axis. But how do we prove this? Suppose let us say this this P, when taken distance from the directrix L and L dash, is meeting at let us say points M and M dash. We can say that PS by PM is equal to E. Similarly, PS dash by PM dash is also equal to E, because this focus has corresponding directrix, this focus has corresponding directrix. Now, if I take difference between these two, so let us say I take mod of PS minus PS dash. So, what will this give me? It will give me mod of PM minus PM dash, okay, into E. Now what is PM minus PM dash? That means it is the distance between these two directrices. What is the distance between these two directrices? It is 2a by e. So we can say that it is equal to 2a by e into e. So e will get cancelled, we will get 2a. So SP minus S dash P when taken mod is always equal to 2a. It is a property of hyperbola. Okay. So now next equation of the auxiliary circle. We know that auxiliary circle is always having the main axis as the diameter. In ellipse also it is having the major axis as the diameter, major axis is the main axis there, and in hyperbola transverse axis is the main axis. So having the main axis as the diameter, if we draw a circle, it is called as the auxiliary circle. Okay. So basically here auxiliary circle is going to be somewhat like this. This will be our auxiliary circle. Okay. So we have understood the basic fundamentals. Now on this context of the star marked property, I will give you much more clarity. Suppose let us say there are 2 points here, there is A here, there is B here. Now there is a point P which is varying such that PA minus PB is always a constant. So PA minus PB is always a constant. Now what would be the locus of P? What would be the locus of P here? So to understand this, we need to understand 3 different cases. One is K less than AB, other is K equal to AB, and the third case is K greater than AB. These 3 cases we need to understand. Now if you look at the earlier case, here we understood that difference between these two is always 2a. So distance between SP and difference between SP and S dash P is always 2a. But if we take the distance between the foci, see S and S dash, so what is this distance? S and S dash is 2a into E. So here if you notice, this 2aE is definitely greater than 2a. So that means this length must always be less than 2aE, which is the distance between the foci which are the fixed points. So that means here when our K is less than AB, we will get hyperbola. Only for this case we will get hyperbola. But hold on, do we get the complete hyperbola? No, we will get only one branch. Okay. So which may be like this. Okay. So we may get a branch of hyperbola like this, but we will not get complete hyperbola. When we put only mod on this, then we will get both branches, otherwise we will get only one branch. But algebraically if we are solving, then you may get the equation of hyperbola, but it will not tell you which branch it is. Equation does not tell you, equation always gives you both branches. So that is why it is also important to understand the geometry. Now let us look at the other case. What happens if K is equal to AB? So if K is equal to AB, it means PA minus PB is always AB. So where should P lie? Just think. So I will do this in green. Suppose if I join A and B on this line, if P is somewhere here, then PA minus PB will always give me AB. So that means starting from this point till infinity, if I take any point on this ray, I will get all points which satisfy this condition. So when K is equal to AB, I will be getting a ray, which is also part of the line joining A and B. Okay. Now if K is greater than AB, we will get nothing. Why do we get nothing here? Because here we can understand that P forms a triangle with A and B. So, PA minus PB, that is difference of two sides, must always be less than the third side. So, if P is outside anywhere, if P is not on the line, then PA minus PB must always be less than AB. If P is on the line, PA minus PB is equal to AB. So, which means K can never be greater than AB, it is not possible. Satisfying this condition, if K is greater than AB, we will not get any point. Okay. So, algebraically if you blindly solve, you may get an equation, but be careful when you are doing blind algebra. Okay. So, this is some basic idea which you can be, which can be used in chapters like complex numbers also. Sometimes questions based on these ideas come. So, if you have geometric clarity, you can answer them. Okay. Come on, take a picture of this also. Okay. So, here basically we have understood what is the setup and what are the standard ideas. Now, let us understand one more concept which is called as the asymptotes. Okay. So, we also have studied asymptotes in earlier probably in functions chapter, especially when we are learning the graphs of exponential functions, logarithmic functions or tan functions, tan theta, sec theta, cosec theta, cot theta or tan inverse, cot inverse, all these functions we have learned asymptotes. Now, let us just take a quick review of the asymptotes. So, basically asymptote is a line to which the curve approaches. Asymptote is a line to which the curve approaches indefinitely. Asymptote is a line to which curve approaches indefinitely. Now, there can be three types of asymptotes. One asymptote is horizontal asymptotes. One could be vertical asymptotes. The other could be slant asymptotes. Okay, that means inclined asymptotes. Now, we get horizontal asymptotes if limit x tending to either infinity or minus infinity, f of x tends to a constant k, and k should be a finite constant. If this happens, then our curve is going to tend to a constant as x tends to infinity, that too horizontally. Okay. Now, for vertical asymptotes, if limit x tending to any particular value, let us say a, f of x tends to infinity for any particular value, at any particular value a, if f of x tends to infinity directly, then that means our graph is going to blow off. Okay. So, this vertical asymptote may look like something like this. Okay. So, basically the graph will approach a straight line which is vertical. Now, in the other case where slant asymptotes are there, what happens is limit x tending to plus infinity or minus infinity, f dash x will tend to a constant. Okay. Basically derivative will tend to a constant, that means the curve will approach a line. So, suppose if there is a line like this, the curve is going to approach either from above or from below depending on the situation. Okay. So, if this line is let us say y equal to mx plus c, so we can say that along with this condition we can also say that limit x tending to infinity, f of x minus mx will always tend to a constant c. Okay. So, basically this slope is basically m and this is basically c. Using these two ideas, you can also calculate slant asymptote of any curve. Remember, any curve, okay, not just hyperbola. You can find slant asymptotes of any curve using these two ideas. Okay. So, basically these three ideas will give you clarity of what kind of asymptotes you are dealing with and how to calculate them. Okay. So, come on, take a note of this. Now, in hyperbola, what is the context of the asymptotes? So, you might have got this confusion also that parabola is also a open-ended curve, hyperbola is also an open-ended curve, and both may look similar, but what is the difference between parabola and hyperbola? The difference is the asymptotes. Geometrically, difference is the asymptotes. So, here I will explain you the idea using the asymptotes. Okay. So, let us say we have this one x axis. Okay. So, we have one x axis and we have one y axis. Okay. So, x axis, y axis. Let us say this is my a comma 0 point and let us say this is my minus a comma 0 point. Okay. And now, let us say I have taken one line here. Okay. Okay, it looks like one line. Okay. And let us say I have taken another line here. So, there are two lines. Now, the curve hyperbola here at this point will have slope which is not defined. That means, here it will be vertical, tangent will be parallel to y axis here, and it bends and it approximates itself with the line. Similarly, here also it bends and it approximates itself with this line. Okay. So, these two lines are basically the slant asymptotes of hyperbola. So, if you have understood this third step, you can derive the equations of hyperbola on your own. On this standard equation, okay, so on this standard equation, you can derive the equations of asymptotes on your own. Okay. But here I will give you one simple tip to remember the equation. Okay. Now, similarly here also the curve will be somewhat like this. So, if you notice what is happening to the curve, it is approaching the line indefinitely. Indefinitely means there is no limit, it is extendedly approaching the curve. So, here it may look like it is going to touch the line after some time, but if you go there and zoom it, it will still not touch. It will keep on approaching indefinitely. It will never touch, it will never cross also, it will keep on approaching. This is the main idea of the asymptotes. So, here we have defined asymptotes. Now, let us look at the equations of the asymptotes. Okay. So, before I go for the equations, there is also one more important point that I want to explain. These asymptotes are basically the limiting lines of the curve. They limit the lines. Okay. So, there are some important ideas which I will discuss now. Suppose let us say from this region I have taken a point P here. Okay. Now, tell me through this point P, how many tangents can be drawn to this curve? Just think. How many tangents can be drawn through P to this curve? So, you might be thinking that 4 tangents can be drawn. No, that is wrong. So, for that I have taken a stick here. I will explain it with the stick. Okay. So, here let us say from the point P. Okay. So, from the point P, if you are thinking we can draw a tangent like this. Okay. So, let us just imagine a line like this. Now, when I am tilting this, you can notice that when I am rotating this, you can notice that this line with the stick is going to intersect the asymptote. Now, if it is intersecting the asymptote, there is no way it becomes tangent, because at this point the curve has automatically become line, because curve is approaching the line. So, if curve is acting as a line and I am taking this as one tangent, it cannot touch it. So, this line has to cut. So, from here to here we cannot get a tangent, but from here to here we can get a tangent. So, that you can clearly visualize here. So, here it is possible that it touches. Again one more idea, from here to here in similar lines we can say that tangent does not exist, but from here to here we can say that one tangent exists. So, from any point P in this region, how many tangents can be drawn? We can draw only two tangents and one each to the branches, both branches. To this branch one tangent, to this branch one tangent. Okay. So, this way we can understand the importance of asymptotes. So, let me just explain it for the other regions also. So, let us say I have taken one point P here. From this point P, how many tangents can be drawn? Again only two, one to this branch, other also to the same branch. So, that means from this region we cannot draw tangents to the other branch. Okay. So, from this region if I try to draw a tangent, you can notice that it is going to intersect, it is not going to touch. So, similarly here also it is going to intersect, it is not going to touch. So, we can clearly understand that from this location, that means from this region, from any point we cannot draw tangents to this branch. Okay. Now, similarly let me take another region. So, from any point here, that means from this region we can draw two tangents, one to this branch and one to this branch, that we have understood. Similarly, from this region we can draw tangents to only this branch, not to the other branch. Okay. So, here these lines, these asymptotes are basically acting like limiting lines. So, here we can understand that if I let us say take this line and rotate this like this. Okay. So, we can get this line, and again if I keep rotating this we will get this line. So, all tangents must be varying between these two lines only. Okay. So, I hope you have understood that idea, all tangents must be varying between these two lines. So, that is the main beauty of this asymptotes. Okay. So, asymptotes are basically the limiting lines of the curve. Okay. So, so using these we can understand how to understand the asymptotes. So, this is basic simple geometric significance. Okay. Now, let us try to understand the equations of these asymptotes. Suppose if I have the equation of hyperbola as this. Okay. X square by a square minus y square by b square equal to 1. So, if I take this 1 and put 0 in place of 1, I will get equations of asymptotes. So, basically, so that means x square by a square minus y square by b square equal to 0 will give me the equations of asymptotes. So, earlier also I have explained the main concept of asymptotes. So, using also this third point, you can derive equations on your own and you are going to get the same equations. Now, here there are two equations, it is equation of pair of straight lines. So, that means this equation will become y equal to b by a into x, and this equation will become y equal to minus b by a into x. Okay. Now, using these equations, we can also get the angle between the asymptotes. So, if I take this angle as theta, this angle also will become theta because the diagram is symmetric. So, here we know that the slope of this line is b by a. So, theta will be equal to tan inverse of b by a. So, what is the angle between asymptotes? Angle between asymptotes is going to be 2 into tan inverse of b by a. So, this is one fundamental idea that we have to understand about the asymptotes. Asymptotes are basically limiting lines, and this is how we get the equation of asymptotes. Also, there is one more idea. If L1 equal to 0 and L2 equal to 0 are equations of asymptotes, then L1 into L2 equal to 1 will give me equation of hyperbola. Okay. So, that means using also equations of asymptotes, we can derive the equation of hyperbola. So, this is some fundamental. Of course, we are going to revise all of them towards the end of the lecture, but these are the basic ideas. What are the asymptotes? What are the asymptotes in our context? What is the geometric meaning? What are the equations? If asymptotes are given, how to find hyperbola? Okay. Come on, quickly take a note of this. This page also. Okay. So, now in this context, there is one more importance. Suppose let us say we have one hyperbola here. So, here let me take one compressed hyperbola. This is my center, this is one asymptote and this is my other asymptote. Okay. Now, let us say the hyperbola is somewhat like this. Okay. So, here if you notice, it looks like parabola. The shape may confuse you that it is parabola, but it is not. It is the hyperbola. So, here because it is a compressed hyperbola, the conjugate axis is going to be a very small conjugate axis. Okay. So, in fact, it will not be even this much long, it will be very small. Okay. So, very small conjugate axis. Now, why are we discussing about the conjugate axis? So, now I am going to explain you why it is called as the conjugate axis. So, by taking this ends of conjugate axis as the ends of transverse axis, I will repeat, by taking conjugate axis as the transverse axis, by taking transverse axis as the conjugate axis, if I draw another hyperbola, that means I want this to be the main axis. So, if I draw another hyperbola having this axis as the transverse axis and having the transverse as the conjugate axis, the hyperbola will look like this. Okay. So, we can take the points like this. Let us say this is A dash, this is B, this is B dash. So, we have two hyperbolas here. One is the blue hyperbola, other is the red hyperbola. So, here A dash is basically transverse axis for the blue hyperbola, but for red hyperbola it is the conjugate axis. And similarly, BB dash is conjugate axis for the blue hyperbola and for red hyperbola it is the transverse axis. And these two hyperbolas, the blue one and the red one, are called as the conjugate hyperbolas. These are mutually conjugates because they have exchanged their axes, they have swapped their axes. Your transverse is my conjugate, my transverse is your conjugate. So, they basically transversed them, they basically shifted them, swapped them. So, we can call them as conjugate hyperbolas. Okay. So, now you have understood that BB dash is basically the main axis of the conjugate hyperbola, that is why we call BB dash as the conjugate axis. Okay. So, here I have explained you why it is called as the conjugate axis. Now that you have understood the main process of this, how to get the equation of the conjugate if you know the original one. Okay. So, now let us go back to the earlier version of the hyperbola. So, here in place of 1, if I write 0, I got the equation of asymptotes. Now, in place of that 1, if I put minus 1, I will get the equation of the conjugate hyperbola. For example, here equation of this red hyperbola will become x square by a square minus y square by b square equal to, in place of 1, I am putting minus 1. So, it becomes my equation of conjugate. So, what is the original hyperbola here? Original hyperbola is x square by a square minus y square by b square equal to 1. So, now here also if you try to simplify this by taking minus sign to the LHS, it becomes y square by b square minus x square by a square equal to 1. Okay. So, if you look at this equation directly, you can understand also this way. Whatever is having the plus sign will become the main axis, that means it becomes the transverse axis. Whatever is having the minus sign will become the conjugate axis. So, if y square is having plus sign, y axis is the transverse axis and length of the transverse axis to that hyperbola is 2b. And if x square is having minus sign, x axis is the conjugate axis, length of the conjugate axis is 2a. So, again here if you understand the red hyperbola is having a dash as the conjugate axis. Okay, so sorry, here a dash is conjugate axis for the red hyperbola, and here for red hyperbola conjugate axis is too big, so hyperbola is stretched. Okay. Now, here if you observe the blue hyperbola, conjugate axis is too small, so hyperbola is compressed. Okay. So, this way we can understand the role of conjugate axis in defining the shape of the hyperbola. Okay. So, here we have understood this. Now, let me also connect this with the earlier idea. So, if L1 and L2 are the asymptotes, so also if you have noticed both equations, both hyperbolas are having the same asymptotes, both are having same asymptotes. Now, that means L1 equal to 0, L2 are equal to 0 are also the same asymptotes for the conjugate hyperbola. So, here if you want to get the conjugate of this hyperbola, so you just have to put L1 L2 equal to minus 1, then it becomes the equation of conjugate hyperbola. Okay. So, this way we can understand the main idea of the asymptotes, hyperbola, conjugate hyperbola, what is conjugate axis, what is the connection, everything I have explained with even more depth. Okay. So, I hope you are liking these ideas. Come on, take a note of this, also this page. Okay. So, now let me explain one more idea. There is one called as the rotated hyperbola. Okay. So, for example, if we have the original x square by a square minus y square by b square equal to 1. So, here if I swap x and y, I am going to get an equation like y square by a square minus x square by b square equal to 1. This is our rotated hyperbola, it is not the conjugate hyperbola. Conjugate hyperbola is the one where we replace 1 with minus 1. Okay. So, there is a difference between the rotated and the conjugate, but in ellipse, in case of ellipse, if we just rotate this ellipse about 90 degrees, we will get the other ellipse which becomes the conjugate of the original ellipse, but not in hyperbola. Okay. So, now with this I have explained the asymptotes and conjugate in very much depth. Now, let us look at the conjugate hyperbola. So, this hyperbola is called as the conjugate hyperbola. Now, here there is no rule that A must be greater than B or B must be greater than A. In ellipse, we always have major axis greater than minor axis, but in hyperbola transverse and conjugate may vary. Okay. So, that we have seen in the earlier diagram also. So, this hyperbola is basically oriented in this way, and you know how to get the coordinates. Okay. So, here this point will be 0 comma b and this point will be 0 comma minus b and so on, it keeps on happening. So, basically this is the theory that we have developed for that. Okay. So, now if you have observed the center, vertices, foci, all will follow the same pattern. Okay. So, everything that we have done here in the earlier case can also be reflected here just by swapping x and y coordinates. Okay. So, that way we can also understand this. So, it is all simple. Okay. So, now equation of auxiliary circle is x square plus y square equal to b square, it is all same, you can understand it. Now, let us look at some important points that we have discussed. So, here A and B are two fixed points, then the locus of the point P such that mod of PA minus PB is constant is a hyperbola with A and B as foci. Yes? No, it has to maintain one rule. What is it? This constant K must be less than AB. So, K must be less than AB, that is the must condition, otherwise it is not a hyperbola. Okay. Next, these two hyperbola are said to be conjugates of each other. We have understood the main logic behind these two. Next, if E1 and E2 are the eccentricities of the conjugate hyperbolas, mutually conjugate hyperbolas, then this relation is always satisfied. So, this we can understand with this idea. So, in this hyperbola, E square, let us name this as E1 square, will become 1 plus B square by A square. B here represents the conjugate, A here represents the transverse. Now, on the other hand, when we take this y square by b square minus x square by a square equal to 1, b represents the transverse, a represents the conjugate. So, here E2 square will be 1 plus a square by b square. So, whatever is in the denominator must be representing transverse axis. So, here you can understand that when I take 1 by E1 square plus 1 by E2 square, it becomes equal to a square by a square plus b square plus b square by a square plus b square, it becomes equal to 1. So, that is basically the main idea of this eccentricities of the mutually conjugate hyperbolas. Okay. So, now there is one idea of rectangular hyperbola. This we will discuss in the beginning of the next lecture. Okay. So, I hope you have liked the today's lecture. I have tried to explain everything to the point and to the every detail possible. Okay. So, I hope you are enjoying these lectures. If you like the lectures, also you can share positive feedback on the app or in the directly the doubt LMS section or anywhere, even ask a doubt section, anywhere you can also share your feedback. Okay. So, we will meet again in the next lecture. Until then, have a great learning day. Learning shall never stop.